time. Here we are going to look at analog and digital stop clocks. But before we do that, let's look at what is time. Time is basically how long something takes. As simple as that sounds, think about it. A football match has a fixed time. Your favourite movie will have a fixed time. Tests, exams, they have a fixed time. Cooking something in the microwave, very often the instructions recommend a time for you to do so. Breaks at school have a fixed time. Now, the standard unit for time in physics is seconds or minutes, but seconds is the most, the standard unit. You will come across days, you will come across hours, you will come across years in certain topics. But more often than not, we'll be dealing with seconds and we'll be dealing with minutes, especially in a classroom, because you're not going to be doing something experimentally for more than an hour. It's measured with a stop clock. Now what we mean here, because quite clearly you can measure time with a watch, but what we're referring to here is measuring a short interval of time. Okay, so here I have a digital stop clock. What do I mean by digital? The numbers are fixed. They're either that number or another number. The actual definition of digital is on or off or 1 and 0, binary. But in the context of the clock, you can either see that number or you will see another number. Whereas if you look at the GIF in the top right hand side, you've got an analog clock where the hour hand and the minute hand is continuously varying all the way around. So the key here is, what time does this read? Now some students might say, it's 24-hour clock, it's 17:58 and 97 seconds. Somebody else might say, it's 5:58 and 97 seconds. In this regard, both would be wrong. Why? Because there's only 60 seconds in a minute. Now, whilst a stopwatch can measure time, its ultimate purpose is to measure a small interval of time. So it's 17 minutes, 58 seconds, and 97 milliseconds. Or if you want to be more simplistic about it, 17 minutes, 58.97 seconds. So if that's a digital stopwatch, this is what an analog one looks like, where the hand will be continuously varying. Now, on this slide, I'd actually like to introduce you to 3 ideas. And those ideas are zero error, precision, and parallax error. Now let's start with parallax. You are very unlikely to get parallax error with a stopwatch. Why? Highly unlikely. I mean, whether you put the watch here or here, it really doesn't matter. The numbers will look as they are. Now, you would have to go to an extreme, but it is possible to get parallax error with an analog watch, because you might look at the second hand or the minute hand or the hour hand in such a way that might make the time look different. Now, it's highly unlikely, but it is possible. Zero error. Zero error is something that is highly possible with both clocks. What does that mean? Where the stopwatch has not been started from zero, whether it's analog or digital. Now you might think, but it's easy enough to reset it. If that's the case, why is it year in, year out, students make mistakes when using these clocks? I urge you to make sure when you look at an exam question, make sure it's starting from zero. Let me give you a very quick example. If you're doing an experiment with me and you start a stopwatch and I say, whoa, I made a mistake, let's stop. And you stop it, and I fix the experiment and I ask you to start again, if you've not remembered to reset it, you've already got a time. For example, it might have been at 1 second. We've now measured something quickly, it's now at 9 seconds. If you're not paying attention, you'll say 9 seconds, when in actual fact it should be 9 minus 1, 8 seconds, because you're taking into account of zero error. The last concept I'd like to talk to you about, which isn't tested directly, but is often overlooked by students, precision. What is precision? Let's look at a ruler. If you think about a ruler, the smallest increment on a ruler is 1 millimeter. If I was to measure a pencil, for example, and it was 9.6 centimeters, would you ignore the 0.6? Chances are you wouldn't. You would stick in 9.6. Why is it then, if I had another pencil that was 9 centimeters, the vast majority of students would write 9 and not 9.0? Now you might think, what's the big deal? The 0.0 is telling you that the ruler has a precision of plus or minus 1 millimeter, or in this case, the way I expressed it, plus or minus 0.1 centimeters. It really does matter in practical, not so much in structured questions, and in multiple choice, the examiner's normally taken care of the significant figures and decimal places for you. But it's something you should pay attention to. For example, let's say I was timing you in a race with your friend, and I have a student helping me with a stopwatch, and I'm going to use my own watch. My own watch measures to the nearest second. The stopwatch measures in milliseconds, but let's keep this example nice and simple. Let's say you run a race and you finish in 9.2 seconds, but your friend finishes in 9.8. Quite clearly, if I've got my student using the stopwatch, you win. But if we're using my watch, it would be a draw. Now you may go, whoa, why? Because my watch only measures to the nearest second. So my watch will make it look like you both came in at 10 seconds. Okay? So precision is important. Precision helps get, a level of accuracy within our results. Let me give you one last example. When you do the light topic, you will have things like refractive index, and you'll be asked to calculate angles. If you've done this before, you might be familiar with angles of 28.26 degrees. You write that in an exam, invariably we'll let it slide. But I want to leave you with this thought. When you use a protractor, when's the last time you used a protractor that measured to 0.26 degrees? The precision on a protractor is 1 degree.